We've learned about spanning trees, and in this lesson we're going to learn about minimum spanning trees. So this starts out here with a statement, and let me go ahead and read it and then we'll talk about it. It says, every spanning tree of a graph with n vertices has n minus 1 edges. Now, is that true? Do we really know that? Well, yes, because we talked a while back about any tree at all is going to have one less edge than the number of vertices. Okay, so if it's a spanning tree, it's a tree and it goes through all n vertices, then yes, it's going to have n minus 1 edges. Okay, so let me start again here. Every spanning tree of a graph with n vertices has n minus 1 edges. So there's no reason to prefer one spanning tree over another if the only goal is to include as few edges as possible, because all spanning trees will have the same number of edges. Okay, so there's nothing to say that one spanning tree would be any better than any others. However, maybe we would have a situation where the edges would have different edges might have what we consider different costs. So for instance, look down here. What I've done here is we started out with a graph, but something that's been added here that we haven't seen before is that there's a number on each of these edges. And so maybe it's the cost of going across a bridge, or maybe we don't know what it could be, but it could be different things in different situations. But maybe there's a certain cost to each edge and they are different. And so in that case, we would then be interested probably in finding a spanning tree, a tree that will include all of the vertices. Find one that has the lowest cost. So that's what this section is all about. So here's an example. In broadcasting a message across a network, the sender maybe would be required to pay for, let's say, bandwidth. Okay, so different communication links might have different costs depending upon their length, congestion conditions, or the quality of the channel. So what we might want to do then in that case would be find a spanning tree that has uses the edges that would represent the lower cost edges and still be able to span the entire graph. So this says here, when edges have varying costs, a natural goal is to find a spanning tree with the smallest total cost, which is called a minimum spanning tree. So if we're going to have edges that have different numbers associated with them, then we don't have the same kind of graph as what we've been working with up until now. So instead of just a regular graph with just vertices and edges, now we have these weights along these edges. So this would be called a weighted graph. So here's the definition of weighted graph. A weighted graph is a graph G that is made up by the two sets that include the vertices and the set that includes the edges. That's just what we're used to for a graph, but along with a function, we'll call it W, and that function goes from the domain of the edges to a range of real numbers. The function W assigns a real number to every edge. So basically we're just saying we have a graph like what we've worked with in the past, but we've added to that in that we have a real number assigned to every edge. That would be called a weighted graph. Now, if we take a subgraph of any weighted graph, we can find the weight of that. So let's look at this green subgraph. That is looks like it is a tree, but a spanning tree, but let's even not worry about that and just look at it as a subgraph. And if we were to ask, what's the weight of this green subgraph? We would look at all the edges, all the green edges, and then add up all of those weights that are on the edges. So 1 plus 5 plus 0, and then a 3 and a 2 and a 1, and that would give us 12. Here's, we start with the same graph, the same weighted graph. All of those weights are the same, but we have a different spanning tree. And let's add that up, the weight of the blue subgraph. And so that would be 1 plus 5 plus 3, 1 plus 6 plus 0, so that would be 16. Okay, so we would be able to compare those and say that the green subgraph has a smaller cost than the blue subgraph. So now we can talk about a minimum spanning tree. So a minimum spanning tree of a weighted graph is a spanning tree whose weight is no larger than any other spanning tree of the graph. So you might have expected them to say the minimum spanning tree is a spanning tree whose weight is the smallest of any of the other spanning trees. But we don't say that because it's possible that a weighted graph might have more than one minimum spanning trees. If we have two that have the smallest number possible, then we can't say that one of those has the very smallest weight. But we could say that either one of those has a weight that's no larger than any other spanning tree. So they're just leaving that open, that there might be more than one. But it is what you would guess. We're trying to find a minimum spanning tree with the smallest weight possible. So I'm going to go through this example here, and I'm going to kind of tell you the steps that we can use to find this minimum spanning tree. There's an algorithm called Prim's algorithm, and the instructions are over here on the left. I think what I'll do is go ahead and go through this first without reading all of this. And so I'll go through it, kind of show you what it's all about, and then after we do it, then I'll probably come back and read a little bit of what's in there so that you can see how that's explaining what we've just done. Okay, so here we have a weighted graph, and we know to start with A. So we're going to start with A over here, and we're going to say that A is the only thing in the spanning tree so far. Okay, now we're going to add on to A, so we're going to find an edge that has one side, one edge. We're going to find an edge that includes A, okay, and add that to our spanning tree. So we can look at our possible, what we might call candidate edges. What are edges that we might possibly choose? Okay, we're not going to choose one yet. We're just going to look at possibilities. So, and we're going to make the candidate edges, make those orange. So I'm going to do this where I've shown you there's 4 possibilities for an edge that we might add on, right? Because we know that A is already in the tree. So these are the only 4 edges that have one, one vertex is A. So those are our possible candidates there. So we're going to turn those a certain color. We're turning those orange right here, just to kind of keep track of the possible candidate edges. And for this step then, we look at all of those possibilities and we look at the weights of each of those edges, and you might guess that what we would do is find the edge with the lowest weight, and that's what we would do. So I'm going to choose AG, and I'll make that red because we're saying that is part of our spanning tree. And I chose AG because it has a weight of the smallest amount of 0. From all of those. Okay, so that's the smallest, so I choose that. Now that I've added a vertex, I want to see if there's any more candidate edges for me to add in the next step. Now notice I haven't gotten rid of those other candidate edges, because for my next step I could still choose any of those. That would still be would not have any problem. It'd still be part of a spanning tree, and that's where we're going anyway, is we're keeping those candidate edges from the previous step, keeping them there. And now there's going to be a time where we have to take some away, but we're not there yet, and I'll tell you when we get to that point. But for now, all we're doing is just continually adding more and more candidate edges in there. So by adding this edge that has a vertex G, then G is now part of my tree, and so I have another candidate edge, which is the DG, right? Because I'm going to be growing my tree out. And so I start with A, I get an edge. Now I could grow the tree out either from the side A or the side G. So that's why we have one extra candidate edge now. So I could choose any of these now and grow the tree. I have numbers, weights 3, 1, 6, and 1. Now there's a tie here, and so we would just choose one, whichever one you'd want. So when there are ties, then that's an example of where you might end up with a different minimum spanning tree than I would, and yet they still have the same weights. Okay, so anyway, I'm going to go ahead and choose this edge between A and F. Okay, so that is one of the ones with the lowest weight, so I'll choose that. Now that I've added F into my actual tree, I have some more candidate edges where I could, branch off of in my next step. So I'll make those yellow too. So anything that goes off of F would be a possibility for me to grow the tree. So now these are all of my candidate edges, and I'll take a look now at, between all of those and see which one has the smallest weight. And we have one that has another one that has a weight of 0. So we'll pick that since we want the smallest. So I'm going to pick F and B, the edge between F and B. And because I've added a new vertex, then I'm going to see what if I now have a few more candidate edges that we might use in our next step. And yeah, anything from B on out I could use to now grow the tree. So I'll make these next two edges, EB and CB. I'll make those orange now because those are possibilities too. So now I have a lot of candidate edges, and again I'm going to just look and find the one that's the smallest value, and again we have a tie. So you might choose one over another. I might choose one, you might choose a different one, but I'm going to go ahead and just choose this edge E to B. So that's one of the lower weights. Okay, so I have that. Now, here's what I need to do for the next step. The next step is, again, just, I couldn't add any more candidate edges, but I'll just take what I have there and decide what I want to add for an edge for my tree. So again, I'll look at the weights and I'll find the smallest one. Now I'm going to choose the one that has a 1 by it because that's the smallest value on any of these candidate edges left here. So I'm going to go ahead and draw the line between D and G. Okay, now here's where we have to watch out and realize that we might have to take away some candidate edges sometimes. Notice that when we added this edge DG, we have accomplished the fact that we've gone through on this spanning tree, we have included F and A and G and D. So after D, I wouldn't need to go any further. In fact, if I did take either of these two edges that come out of D, if I use any of those in a later step to add into the tree, then it's no longer a tree, right? Because if I add AD, then now I have a cycle and it's no longer a tree. Or if I add FD, I have a cycle and it's no longer a tree. And again, there's no reason to add those anyway because we've already found part of this tree that already goes through F, A, G, and D. So there'd be no reason to do any more after this from this vertex D. So those two candidate edges that I had there, see those two there, the 1, 2, and 6, those two edges I'm going to take away as candidate edges now. Again, because I don't need them, and in fact, if I added them, it'd no longer be a tree. So I'm going to look at those and say, I don't want them anymore. So I'm going to turn those back into black lines. Those are no longer candidates. Okay? Then for my next step, I'm going to say which edge do I want to add now? Well, I have 3 candidate edges, 5, 2, and 3. The lowest one is a 2, so I'm going to choose that one. So I will add this edge, C and F. Now we might notice again that really this would be all we'd need for a spanning tree, right? Because we've now gone through all of the vertices. So we might just see that now, but officially what we would do is, let's say that we didn't notice that, but we would be checking to see, by adding this new edge, has it made either of these candidate edges no longer candidates? And it has, right? Because by adding that edge between C and F, now not only now have I gotten to C, which was what I needed to do anyway, but if I would turn the CB into a red line, then it's no longer a spanning tree because I have a cycle. Or if I were to take CA and turn that into red and have that part of the tree, it's no longer a tree because I'd have a cycle again. So once I put the CF edge into the tree, then again, these 2 candidates, CB and CA, are no longer candidates anymore, so I'm going to turn those back into black. Now, I know it's harder when you're doing this with paper and pencil because you can't turn things different colors necessarily. You could, but then changing them back would be an issue. So, what I would be doing probably if I were doing this by hand on paper is, for one thing, maybe use pencil. And when I come up with a candidate edge, maybe I would, put like a dotted line or maybe a certain color with a colored pencil. And then once I decide to use that as part of the tree, then maybe I color it in real heavy or something to show that that's no longer a candidate, I'm actually using it. And then at any time when I need to drop something as a candidate edge, then I guess I could erase the dotted line or erase that colored pencil where I had it. So it is definitely more difficult, but it could be done, and I'm sure you could find a way to do it. But anyway, we went ahead and found this minimum spanning tree. We've spanned this graph, and if we were to add up the total weight, we would find that there's no other spanning tree that has any lower weight than this one. There might be another one or more that have the same, but at least we know this is one of the smallest, lowest weighted spanning trees. Okay, now that we've gone over that, now let me kind of read what's up here under Prim's algorithm so that you kind of see what we just did. So it starts by saying the algorithm starts with a single vertex and grows the minimum spanning tree by adding a vertex and an edge in each step. So that's what we did, right? We started with A, and we keep growing the tree by adding a new edge to a vertex that's already in the tree. Okay, so now here underneath it says if T is a partial tree at a particular point in the algorithm's execution, the set of candidate edges to be added next are the edges with one endpoint inside T and one endpoint outside T. So remember, every time we, when we first started with the A, then our candidate edges were all those edges that were connected to A. And so that would be one endpoint inside our tree, which was just only that one little vertex A, and then one endpoint outside. So we started with those, and then each time we added, this again says, the set of candidates edges to be, the candidate edges, I was talking about that one particular step, but just in general, this is saying, each time we have a new part of the tree, we're going to evaluate all of the edges and find all of the candidate edges. Now, in practice, what that ends up being is that some of those from the previous step are going to be left, and then when we add to the tree and add a new vertex in, then that's going to possibly give us some new candidate edges. So basically, each time we're going to add on to the tree, but each time then we'll evaluate to see which edges are candidate edges for the next step. Okay, and then this last part, it says Prim's algorithm selects the smallest weight edge among all the candidate edges and adds the selected edge to T along with the endpoint of the edge that's not in T. So basically we find that edge and then it gets added on into the tree. So that's basically what we did. We're going to do some more examples so you'll see it done more, but that's the idea behind finding this. Now they also have this official algorithm, Prim's algorithm, that is doing what we've just done. So you see it here, and I have an example over here on the right. We're going to go through this example again. I don't know. I don't think I'm going to just look, I don't think we're going to go statement by statement here. I think what I'll do is just use our what we know to be the method here, and just let you know that this algorithm here does do what we're going to be doing. But I won't, this isn't anything that you have to come up with, this algorithm. You have to perform it for us, at any point to be able to find the minimum spanning tree, but you wouldn't have to come up with this yourself. So we won't look real carefully at this algorithm here. But let's just look at the example here, and we always start with A. So I'm going to say that A is inside my spanning tree. And then I want to look and see what are some candidate edges. So I would have any edge that is connected to A. Okay, so I have these 4 edges that are candidates. Those are candidates for us to add into our spanning tree. So of those candidates, we're going to find the one with the smallest weight. So we would use this A to E. Choose that one because it has the lowest weight. So that means we add that edge and we add E. There. It's trying to get E there. So we add E. Now when we add E, we add some more candidate edges, right? So by adding E into my spanning tree, I've now found all of these edges that connect to E are possibilities for us to add the next time. So, and we always kind of double checking, but we don't usually have to worry about getting rid of candidate edges at the very beginning. It's when we start filling up the tree, usually is when we realize, oh, I've already spanned what I needed to span, and if I go further, I'm going to have a cycle. So anyway, at this point, we don't need to take any away. So we just add those 3 new ones. One is of weight 2, one is weight 4, one's of weight 5. And we keep the ones that were already there as our candidate edges. So now of all of those, we're going to check and see what is the lowest weight, and that would be this 2. So I'm going to add that edge that's a 2, and then also add the vertex on the end of that. So F now is also in my tree. Now that F is in the tree, I'll see, are there any other candidate edges that we could go to here for the, any further steps. And so F does connect to this, F can go to A. Oh, wait, sorry, let me see. I was going to say, yeah, this is what I was going to say. I guess I forgot that I did one before the other. What I was trying to say is we've added a candidate edge here. See this one here, the D to F to D? that's a candidate edge that we can add. So I'm making that orange. What just happened a second ago, and I can't go back, what just happened is, if you notice, this edge here between F and A flashed, and then it was orange, it flashed, and then it turned black. Okay, now why is that? Well, as soon as we added this edge E to F, then this edge FA is no longer a candidate, right? Because for one thing, we don't need it because we've already included the vertex A and F. But also, if we did include it, we'd see there's a cycle there. So I should have mentioned that first when we added. It doesn't really matter which one you do first. When you add an edge, do you want to add the new candidates and then after that get rid of those that are no longer candidates, or do you want to get rid of those first and then add the new ones? So I here talked about it with adding the new one first, but as you can see, I had my slide doing it the other way. So we get rid of FA, but we do gain the FD. Okay, so now let's see what we've got. We've got all of these candidate edges, and we're going to look to see which one is the smallest, and the one that's of weight 1 is the smallest. So FD, I'll add that, so that edge is added, and then D now is also added into the tree. Now, when we add D, now that we're a little ways in here, we got to just every single time check. By adding an edge, do we need to take away any of the candidate edges? And by adding this edge, we do have a candidate edge that's no longer a candidate edge, right? Because DE is no longer a possibility. Because for one thing, we don't need it because we already have D and E in our spanning tree. But if we put that into our spanning tree, it would no longer be a tree. So DE now is going to flash and then go away as a candidate edge. So that just stays black now. Okay, so now we've got 3 candidate edges. One is 5, one is 7, one is 6. So we'll take the smallest one, which is the one with a 5. So E and C is going to be added in there. Now, by adding C in there, are there some extra, okay, we're going to need to ask ourselves, are there some new candidate edges we can add in? But then we're also going to need to ask ourselves, are there some candidate edges we need to take away? So let's see which one I decided to do first this time. Okay, I'm again doing the takeaway. So I have to take away that edge that has a weight of 7 because I don't need it, and if I included that, it's going to have a cycle. So I'll get rid of that. So I got rid of that candidate edge, but I do add a candidate edge, right? The CB. That's now a new candidate edge because it hooks up with that spanning tree that we have. So, so now we've got 2 candidate edges. We could either come off of A or come off of C and get one of those edges. So one is of weight 5, one is of weight 6. So we'll choose the smaller one. We'll choose the one 5. So we'll choose that. Now we notice that we've gotten through, we've included now all of our vertices. So that would be one hint to us that we aren't going to have any candidate edges to even, we don't need to be looking for candidate edges, but it also tells us if we've gotten through all of the vertices, then anything that we thought was a candidate edge before really is no longer a candidate edge because that one A, B, that has to go now too, right? Because we don't need it, and if we included it, we would have a cycle. So I'm going to get rid of that one. That's going to turn black again. And now we have our minimum spanning tree. It is a spanning tree. It includes all of the vertices, and it is also a tree. And it turns out that because we used that process, we know that there is no spanning tree of this graph that has a lower weight. It's possible maybe there's one that has the same weight. I don't know in this case if there would be, but you know, we're not saying that's not the case, but we're definitely saying that there's no spanning trees with a smaller weight than this one. Okay, let's do it again. Again, we're going to start with A. So start with A and then look at the candidate edges. So here's all the candidate edges. We're just going to grow from whatever is in our tree. We're just going to grow off of that. So all we have in our tree so far is the one vertex A. So let's go ahead and find the candidate edges for that, and that would be these 4 here. So those would be the possible candidate edges. Now we're going to see and look and see which is the smallest weight, which has the smallest weight, and AD has the smallest weight. So we'll choose that to be part of our tree. And now, because I added D as a vertex in my tree, I may have added some more candidate edges. And I did, because now DF is a candidate edge, because it would be, you know, just growing off of that vertex that's new now in the tree. So that would be possible too. Okay, so now we look at all those candidate edges and find the one with the smallest weight. And it would be that one that we just added as a candidate edge, D to F. So we'll add that, and now let's think if there are some, well, there's going to be some new candidate edges we can add, but already there's going to be an edge we can get rid of, that we need to get rid of as a candidate edge. Do you see which one that is? There's one that will, if we leave it in and never chose it, would give us a cycle, and that's AF, right? So this line here, AF, is going to have to go back to black, because we'd have a cycle if we used that. Okay, so we'll get rid of that candidate edge, but we've gained a bunch, right? All of the other edges that are connected to F would be new ones that we could add in there. So those would be possibilities there. Now we'll see of those, which is the smallest, and looks like 2 is the smallest. So I'll choose that one. So FH is now in there. H is in the tree. And because H is in the tree, we'll see if we have, first of all, if we need to get rid of any candidate edges, and then if we need to, if we can add some. So there's nothing that we would need to get rid of here, right? Because that, you know, there's nothing really connected to H that's already a candidate edge. So by adding H, we're not having to, since there weren't any candidate edges that touched H, then there's no possibilities that we need to get rid of any. So, but what are the new ones then? So here would be the new possibilities, GH and HB. So we've added those. And now we look at all of those and see which is the smallest weight, and it would be GH. So I'm going to add GH in there, and now we've got to think through what do we need to take away, and you know, then also is there anything we need to add? Well, there would be nothing to add because the things coming out, the edges coming out of G, are already candidate edges. So the question we would ask, though, is these edges coming out of G, should they stay candidate edges? And one clue that would tell us that we would want to get rid of them is we notice, look at A, D, F, H, G. All of those on that side of the graph are included in the minimum spanning, in this spanning tree. So there would be no reason we'd need to go from G to F or G to A, because A and F are already in there. So that's one clue, and then we see that if that's the case, then also if we would add one of those candidate edges in there, we would have a cycle. So the AG, which has got a weight of 11, and FG that has a weight of 6, those now need to go away. So that goes away. I don't know why. Okay, there goes the 11 away. That 11's away there. So, okay. Now we're going to see what's left and what is the smallest weight. And we see FE is the smallest weight. That's 3, a weight of 3. So we'll add that in. And now, do we need to get rid of any candidate edges that come off of E? Yeah, you know, that one that has a weight of 10. If we added that in as red, then we'd have a cycle. So we don't want that. So we're going to turn that back to red. But what about the other one coming out of E, E to C? Yeah, that's a candidate edge. So we'll go ahead and add that. Okay, now 5, 12, and 7. We'll choose the 5. And so I'll turn that red. Now, do I have any candidate edges to get rid of? Yes, the one coming out of C going into F. That's no longer a candidate edge because that would give us a cycle. So I'll get rid of that. But I do have the edge coming out of C going into B. That's a possibility. So I'll go ahead and turn that into a candidate edge. So we've gotten through all of the vertices except for this B. And we see that our 2 candidate edges left are both going into B. So we're going to choose the one with the smallest weight, and that would be 4. So I'm going to choose that one. Once I choose that as being an edge in my tree, and so therefore B is now a vertex in my tree, then now HB is no longer a candidate edge. Again, because we don't need it because we've already included all of the vertices, but again, if we did turn it red, we'd see we no longer have a tree since we have a cycle. So we'll get rid of that, turn that back to black. And so this then would be considered our minimum spanning tree or a minimum spanning tree for this example here.